Myself, Dr. Prashant Kumar Bardhan, Professor, Department of Mechanical Engineering, GIS College of Engineering, Kollani. My subject topic is Advanced Welding Technology, ME 703A. Course objectives. After completion of this course, all students will meet the following objectives: to impart knowledge on various advanced welding processes so that the student can apply them in engineering industry applications. To develop the knowledge on the design of welded joints and the quality control of weldments. Course outcome. Upon completion of this course, the student will be able to achieve deeper knowledge of welding materials and technology of welding processes, deeper knowledge of different metals and their properties in welded construction, knowledge of quality technique at production by welding, knowledge of current computer robotic system, and cost for welding operations. Advanced Welding Technology, ME 703A, there are 7 modules. Module 1, Introduction, Review of Welding Processes and Joint Design of Weld. Module 2, Process of Fusion Welding, Arc Welding, Shielded Metal Arc Welding, Gas Metal Arc Welding, Submerged Arc Welding. Module 3, Solid State Welding Process, Pressure Welding. Module 4, Friction Welding, Electron Beam Welding, Ultrasonic Welding. Module 5, Gas Tungsten Arc Welding, Plasma Arc Welding, Arc Welding Equipments, Electrode Selections. Module 6, Welding Metallurgy, has weldability of carbon, plain carbon steel, stainless steel, cast iron, aluminum alloy. Module 7, Welding Defects, Type, Causes, Inspection, and Remedial Measures, Testing of welded joints by visual diagnostic test, radiography, ultrasonography, safe practices in welding. Prerequisites: manufacturing technology, welding technology, joining of metals. CO2 mapping, 4 COs against 12 POs. This is the mapping. 3 is the highest and 1 is the lowest. These are the figures. This is the average figure of COs against PO, and the POs against COs. Average COs. So this is the figure, CPO mapping. The Advanced Welding Technology, ME 703A, Weldability of Aluminum Alloy. By myself, Dr. Prashant Kumar Bardhan, Professor, Mechanical Engineering Department, GIS College of Engineering, Kollani. Weldability of aluminum alloy. Aluminum and its alloy are used in fabrications because of their low weight, good corrosion, resistance, and weldability. Although normally low strength, but some of the more complex alloy, aluminum alloy, can have mechanical properties equivalent to steels. Various types of aluminum alloy are identified and guidance is given for fabricating component without impairing corrosion and mechanical properties of the material or introducing imperfections into the weld processes. Most of the rod grade in the 1, 3x, 3x, 5, 3x, 6, 3x, and medium strength 7C, 3x, that is 7020 series can be fusion welded by TIG, MIG, and oxy-fuel processes. The 5 3x series alloy, in particular, have excellent weldability. High strength alloy, that is 7010 and 7050, and most of the 2 3x series are not recommended for fusion welding because of they are prone to liquefaction and solidification cracking. Material types, the aluminum have the several types of aluminiums. This is 1 3x 1050, 2 3x 2014, The copper alloy, copper added manganese 3x 31003, port 3x 4043A, silicon added manganese 53x 5083, and the 3x 6082, that is manganese and silicon, and the zinc added 7020 733x, and others 83x 8090. Non-heat treatable, green color is non-heat treatable, red is heat treatable, white is not recommended for welding, yellow is alloying element, green is filler welds. These are the aluminum materials, different type of aluminum. This is green filler welds. So filler metal composition is determined by weldability of the parent metal. Minimum mechanical properties of the weld metal: corrosion resistance, anodic coating requirement, nominally matching. Filler metals are often employed for non-heat treatable alloy. However, for alloy lean materials and heat treatable alloy, non-machining fillers are used to prevent solidification cracking. Problem with the welding of aluminum alloy: solidification cracking, liquefaction cracking, reduction of tensile strength in HAS due to grain coarsening, porosity, hydrogen-induced cracking, HIC, and inclusions of oxides. Imperfections in welding. Aluminum and its alloy can be readily welded provided appropriate precautions are taken. The most likely imperfections in fusion welds are porosity, cracking, poor weld bead profile. Porosity. Porosity is often regarded as an inherent feature of MIG welds. Typical appearance of finely distributed porosity in a TIG weld is shown in the photograph. The main cause of the porosity is absorption of hydrogen in the weld pool, which forms discrete pores in the solidifying weld metal. This is the porosity, and this is a heat affected zone. This is the porous material. Typical appearance of finely distributed porosity in a TIG weld is shown in the photograph. The main cause of the porosity is the absorption of hydrogen. With the absorption of hydrogen, the weld pool, which forms discrete pores in the solidifying weld metals. Porosity. The most common sources of hydrogen are hydrocarbons and moisture from contaminants on parent material and filler weld surfaces, and water vapor from the sealing gas atmosphere. Even trace levels of hydrogen may exceed the threshold concentration required to nucleate bubbles in the weld pool. Aluminum being one of the metals most susceptible to porosity. To minimize the risk, rigorous cleaning of materials surface filler weld should be carried out. 3 cleaning techniques are suitable: mechanical cleaning, solvent degreasing, chemical etching cleaning. What is mechanical cleaning? Weld brushing, stainless steel brushes, scraping or filing can be used to remove the surface oxide and contaminants. Degreasing should be carried out before mechanical cleaning. Solvents, organic solvents can be used to remove the greases. Chemical etching, a solution of 5% sodium hydroxide can be used for batch cleaning, but this should be followed by rinsing of nitric acid and water to remove reaction product on the surface. Porosity, atomic percentage of hydrogen increases, weight of percentage of hydrogen by weight. Temperature increases, formation of aluminum oxide, which acts as nuclei of gaseous pores. Sources of hydrogen, surface oxide film, lubricants on the filler wear, electrode coating from the sealing gas. From the use of excessive current in gas metal arc welding, which cause excessive turbulence in weld pool, resulting in large continuous forces. So hydrogen absorption automatically increases, porosity also definitely increase. This is the figure. Remedies, hydrogen porosity, surface cleaning is the uh, one of the top method. Cleanness of the filler wear, increasing the surface to volume ratio, using a larger diameter filler wear, tunneling, limiting the current per pass, gravitational mode of metal transfer, improving inert gas shielding, solidification cracking. Cracking occurs in aluminum alloy because of high stress generated across the weld due to the high thermal expansion, twice that of steel. Thermal expansion is twice that of steel, and the substantial contraction under solidification, typically 5% more than an equivalent steel weld. So contraction also typically 5% more. This is a cracking. This is the heat effective zone. And this is the cracking. Cracking occurs due to high stress generated across the weld due to the thermal expansion. Solidification cracking. This is solidification cracking. Solidification cracking, wide brittle range, low strength, temperature gradient, ductility and tensile strength. Temperature increases, this ductility and tensile strength, ductility decreases. Tensile also decreases. Condition, metal must lack ductility. Tensile stress develop as a result of contraction must exceed the corresponding fracture stresses. Long freezing range alloy, long interval between nil ductility temperature, covalent temperature occurs near liquidus. Occurs usually in TIG welding, MIG, electron beam welding, with aluminum, magnesium, 3x alloy, magnesium 0.5 to 2.5%. This is figure. This line is the ductility, and this may be tensile. White brittle range. This is white brittle range. Solidification cracking. Remedies, lowering the solidification temperature range, bringing the dilution, base metal plus filler metals nearer to the eutectic compositions, that is using a higher alloy content filler, that is aluminum 5%, silicon, aluminum 12% silicon. Aluminum 5% silicon to aluminum 12% silicon. Low heat input, fast welding speed. Grain refinement, grain boundary area inversely proportional to grain dia D. Therefore, if the grain dia is reduced, residual intergranular liquid film is also reduced. Intergranular cohesion is increased. Method: adding of titanium, boron, or other alloying elements, steering on the Whirlpool ultrasonic electromagnetic vibrator. Liquefaction cracking occurs when welding high-strength aluminum alloy of the beryllium or aluminum magnesium zinc type. This is the fusion boundary, Whirlpool magnified. This is a base metal. This is Whirlpool grain crack. This is crack. This is crack. Associated with the presence of low melting constituent in the structure occurs at relatively low heat input areas. Remedies by use of low melting point filler metal, increasing the welding speed. Liquefaction cracking. Poor weld beat profile, incorrect welding parameters setting, or poor welder technique can introduce weld profile imperfection such as lack of fusion, lack of penetration, and undercut. The high thermal conductivity of aluminum and the rapidly solidifying weld pool make this alloy particularly susceptible to profile imperfections. Heat affected zone for precipitation hardening alloy, there is dissolution or coarsening of precipitation precipitates. High heat input and preheating increase degree and width of the heat affected zone. Tensile failure occurs in the heat affected zone. Post-weld heat treatment required. For non-heat treatable alloy has heat affected zone degradation is limited to recovery, recrystallization, and grain growth. Weld metal is the weakest part due to residual stresses. Post-weld heat treatment not required as welded condition can be used. Remedies has heat affected zone degradation in heat treatable alloy, multi-pass welding, close control of inner pass temperature, elimination of preheating, fast welding at low currents, post-weld heat treatment, solution heating, quenching, and aging. Remedies. These are the remedies. Weldability of aluminum. Weldability is a function of three major factors: base material quality, welding processes, and design. The base metal weldability of aluminum alloy in terms of mechanical properties, degradation, in both the weld region and heat affected zone, weld porosity and susceptibility to solidification cracking and liquefaction cracking. It provides an overview on welding processes, including gas metal arc welding, gas tungsten arc welding, resistance spot, seam welding, laser beam welding, and various solid state welding processes. Weldability of aluminum, a review on joint design is also included mainly in the general factors associated with the service weldability fitness. Here we also should consider brief idea about the selection and weldability of non-heat treatable aluminum alloy, heat treatable aluminum alloy, aluminum lithium alloy, and aluminum metal matrix composites. Aluminum metal matrix composites, aluminum silicon carbide, also the metal matrix composites. So we have to consider the other factors also, or the other materials. Questions. Which welding is suitable for aluminum? One of the most popular welding process of aluminum is gas tungsten arc welding, GTAW, otherwise known as tungsten inert gas welding. GTAW is a great process for aluminum because it does not require mechanical wear fitting, which can create fluidity issues. Number two, how do you prepare aluminum for welding? To summarize, take the following steps before welding aluminum. Remove oil, grease, water vapor using a solvent or mild alkaline. Remove surface oxides with a wire brush or strong alkaline or acid. Assemble the joint. Keep the joint dry. Weld within a few days. Otherwise, formation of oxides. Question third, why is aluminum difficult to weld? Anodized coating gives the aluminum an attractive, uniform, hard surfaces that is also highly resistant to corrosion. The characteristics of this aluminum oxide coating make it very difficult to weld. First of all, aluminum oxide is an electrical insulator, so starting and maintaining a stable arc is difficult. What electrode is used for aluminum welding? That is tungsten. For this reason, pure tungsten or zirconated tungsten are recommended for aluminum welding. In addition, the electrode diameter of AC welding has to be significantly larger than using DC. It is recommended to start with an electrode that is 1 by 8 inch, 1/8 inch less 3 millimeter and adjust as needed. So, four questions was discussed. So, next we have completed on another question. How strong is welded aluminum? Most fabrication codes require a minimum as welded tensile strength, that is 24 KSI, 165 MPa, which is a significant degradation as when designing for the non-heat treatable alloy. The designer must not use parent material properties in design. Does welding weaken aluminum? In most cases, a weld is an aluminum alloy is weaker than the alloy being welded. The weld is not as strong as the present materials, which a lot of people don't realize, says Frank G. Heat-treatable series of aluminum alloy are 2000, 6,000, 7,000, and non-heat-treatable alloy are 1,000, 3,000, 4,000, and 5,000. The weld is not as strong as the apparent metal materials, which is a lot of people don't realize. So heat-treatable series of aluminum alloy are 2,000, 6,000, 7,000, and the non-heat-treatable alloy are 1,000, 3,000, 4,000, 5,000, etc. So this is the uh, end of the weldability of subject to weldability of aluminum alloy. Thank you.